So the student asks the question, a hollow steel ball of diameter 5.4 meters just barely floats in water. What is the wall thickness of the ball? And it gives us the density of iron. So how do we solve this? Well, it's a little tricky, but not too bad. So what we're going to do here is we're going to, I'll paste this up here first. Let's go ahead and write down what we have and what we're looking for. So it gives us a couple of things here. It says this is the diameter, and it gives us the density of iron. And it asks us about the wall thickness. So let's write that down. So we got the diameter is 5.4 meters. The density of iron is 7.87 grams per centimeter cubed. It's not our standard units that we've been using, so we're going to be careful of that. And then it asks for the wall thickness. So I'll just call that T. So what is going on here? So there's a lot more information we have than meets the eye. So for example, if we were to draw a picture here of this, we got some water in some sort of container, and we have this ball. Now, what's important is that it says it just barely floats, just barely. So that conveys a couple of things. So first of all, floats is important. If it floats, we're looking at a free body diagram where the force of gravity would be equal to the buoyant force. So that's important to know because it's floating. But the fact that it says it just barely floats, what that's trying to get across to us is essentially the entire sphere is covered in water, right? But it's not sinking, right? What this is trying to tell us is that the density of this sphere should equal the density of the water. That's what this little phrase tells us here. Okay, so I think we pulled out the information that we know. Oh, there's one more piece. It's also a hollow steel ball, right? So what that means is if we're looking at our sphere here, if I kind of blow it up a little bit, do a little cross section of it, it's hollow. That means there's nothing inside of it. And so usually when people say nothing, they mean like air. But in this case, it doesn't say anything about anything being inside here. So we can't even assume air. We have to assume it's completely empty, just as hollow. So here, we have a radius, because no matter what this thing is, if it's hollow, it has a certain thickness, right? And this thickness here, right, from here to there, that's what we're trying to find, that's the T. And so in this case here, we're going to have essentially two radiuses, right? We'll have the radius of the inside sphere and the radius of the outside sphere. I'm going to call the radius of the outside sphere just our normal radius. So I'll call that just, radius of the sphere, r sub s. But the inside one, we have to call something else. I'm going to call it the radius of the, emptiness, basically. Because it's the stuff on the inside. There's nothing there, so I'm just going to say the radius. I couldn't say inside radius, outside radius, whatever. It's just a label. Now, how do we find the thickness? Well, it's pretty obvious from the drawing here that if you want to find the thickness, well, you just take the radius of the entire sphere and you subtract the radius of the smaller sphere. So in this case, it's called r sub e. Well, good news. R sub s is pretty obvious. It's basically written up here. We just cut this in half. So let's say r sub s here is half of 5.4, so that'd be 2.7 meters. All right, let's write this out here to make sure everybody's clear. All right. So 5.4 divided by 2 is 2.7. All right. So we got that. So we're most of the way there. We just need to find this inside radius. Well, that's what's going to be a little tricky because it didn't just give it to us. But we do know that it just barely floats, and we know the density of iron. So what we're going to do here is if it just barely floats, it tells us several things. That the two densities are the same, right? But if it floats, the volume of water that is displaced should be equal to the volume of the object. I wrote this backwards from what I had up there earlier. So that's because it's floating, right? Well, because it's floating, we get the top equation. Because it's entirely submerged, we get the bottom equation here. So the volume of the sphere should equal the volume of the water displaced, right? And that's what it's trying to emphasize, that it's floating, number one. So that's good knowledge. And that's the floating essentially tells us this, and then the fact that it's completely covered tells us the densities are the same. So now, that would mean, equals mv, that the mass of the sphere, the total mass of the sphere, should equal the same as the mass of the water that is displaced, right? Because if the density is equal, volume is equal, well, mass has to be equal. There's no other choice there. So since we know the mass is equal, what we can do is we can figure out the mass of our sphere. Well, why do we want to find the mass of our sphere? Well, in the end, we don't have enough information to directly find E, so we're going to have to find it another way. Well, essentially what we can do is we can find the total volume of the whole sphere, and we can break the volume of the sphere up into two pieces. So the volume of the sphere, plus we have the volume of the empty part, plus the volume of the iron part. So that would give me my total volume. So I have the volume here, and then I have the volume of the iron out here. So if I can figure out these volumes, say this volume here and this one, I can solve this for the volume of the empty part, and we know our formula for volume has a radius in it, right? So we can use that radius and go here. So those are our steps. So essentially, we have 3 steps to do. So in order to get to the thickness, we have to find the volume of the empty part. In order to find the volume of the empty part, we need the volume of the sphere, which is an easy calculation, and we need the volume of iron. Well, volume of iron is not directly shown either. So let's go ahead and go through these one at a time. So let's do volume of the sphere, that's easy. Volume of the sphere is just volume of a sphere, which is 4/3 pi r cubed. Okay, cool. Volume is 4/3 pi r cubed. You can go ahead and calculate that. So this is r/s. So in this case, I'll put 4/3 times pi. Well, I'm just going to leave pi there. Well, I was going to solve it, but I decided against it. So 2.7 in this case, cubed. So that will give me a volume, and then I can subtract out the volume of the iron once I get it. So let's just go ahead and do this. Pi times 2.7 cubed. So I get a volume here of about 82.45 meters cubed, which, if you didn't notice, is an enormous volume. Now, how do we find the volume of the empty part? Well, we get that from this equation, so we've got to find the volume of iron, and so we just use our density formula here to find the volume of iron. Because it gives us the iron's density, and we know that's mass divided by the volume of iron. Now, we have to be very specific here. Because we have volume of the sphere, volume of water, volume of iron. So we know the density of iron is 7.87. And in order to find the volume of iron, let's rearrange this guy. We need to know the mass of iron. And this is where our assumptions come back in. Here, we said that the mass of the sphere should equal the mass of the water displaced. That makes sense. But what did we assume was inside the sphere? Well, we assumed that nothing was inside the sphere. And if that's true, the total mass of the sphere is really just the iron, right? Because there's nothing else in the sphere. Now, the mass of the iron is the same as the mass of the sphere, which ends up being the mass of the water. But the volume of the iron is not the same as the volume of the water, right? So be very careful there. So how do we find this mass of the water? Well, we just plug in what we know for water here. So what we end up with is, I'm going to substitute in this stuff for water here, essentially. The mass of water, so I'd say mass of water equals, rho v. I'm going to plug that in here, which I can then plug in there, right? So we have the density of water times the volume of the water divided by the density of iron should give me my volume of iron. Now, the issue is I have the density of our sphere in 7.87 grams per centimeter cubed, and our default units are slightly different. I'm not going to take the time to convert this. What I'm going to say, if you guys don't know this, is the density of water is 1,000 kilograms per meter cubed, but it's only 1 gram per centimeter cubed. Right? So you can convert that, or you can look it up, or just memorize it, honestly. So the density of water is 1. The volume of water displaced would be our volume that we just calculated here, because it's the same as our sphere volume, so it's 82.45 meters cubed in this case. This is 1 gram per centimeter cubed. Okay. Oh, wait. Divided by the density of iron, which is 7.87 grams per centimeter cubed. Now, you'll notice that meters and centimeters are not the same unit, but this units will cancel with those, so nobody cares. So essentially, we just need to take this number divided by 7.87. So we'll do that, 7.87. And I get the volume of the iron to be just 10.47 meters cubed. Okay, so now that we've done that, we've got our volume of iron. So now let's go ahead and solve this equation. So I'm going to hop over to more screen here. So the equation we're trying to solve is the volume of the sphere equals the volume of the empty part plus the volume of the iron. So we got the volume of the sphere as being 82.45 meters cubed equals the volume of the empty part plus the 10.47 meters cubed. So now to find the volume of the empty part, we subtract 10.47 both sides. And we get a volume of 71.98 meters cubed for the empty part. So now what we can do is we know the volume, so we can work backwards, because eventually we want to be able to solve this equation. The thickness of the shell is equal to the thickness of the sphere, or radius of the sphere minus the radius of the empty part. We know the radius of the sphere. I'll write that on the screen. So radius of the sphere is 2.7 meters. So now we set this equal to 4/3 pi r cubed, and solve for r. So I'm going to do 3/4 times 71.89 or 98. And then divided by pi. So I could have left 4/3 and pi in there, but ultimately I decided against it. And that should equal r cubed. So that means I'm going to have to take the cubic root. That will give me the r of the empty part, right? That's what I'm finding here, volume of the empty. So when you're doing this in your calculator, I think the part inside our root sign is pretty easy. 3/4 times 71.98 divided by pi. This. Okay, so I'm getting, or the thing you have to take the cubic root of, I'm getting 1. So the thing I need to take the cubic root of, so r cubed ends up being about 17.18 meters cubed. So in order to take the cubic root, you can do that, but also remember that when you want to do this, if you don't have a cubic root button on your calculator, you might be struggling going, I don't know how to do that. Well, if you have a cubic root, then it's pretty easy. If not, what you need to do is you need to raise it. Check, make sure I'm not saying something crazy here. Yeah. So taking a cubic root is the same as raising it to the 1/3 power. So in your calculator, it's kind of like a side note. If you take the 17.18 and you raise it to the 1/3 power, then that's the same as taking a cubic root. So when you do that, you get RE as 2.5, say 2.58 meters. Okay. So now let's find the thickness of the shell. So R sub S is 2.7 minus R sub E is 2.58. So the thickness of the shell is 7 minus 2.58 is 0.12 meters. So that is our answer. You should notice that that's 0.2 or 0.12 meters. So that's not very thick. That's like 12 centimeters. It's less than a foot. Does this seem reasonable? Well, yeah, it's not going to be very thick, but you have to understand, like these dimensions that this problem gave us are enormous. Now, I went through this as carefully as I could, and hopefully I didn't make any mistakes. Once you kind of get these concepts, a problem like this can be pretty easy if you know where you're going and where you're coming from. And if you know, okay, this volume is equal to that volume, so that means it's flowing and the density and all that stuff that I went through. What I want to say here about this problem is, if you're looking at this problem going, dang, is that supposed to be a multiple choice question? Yes, it is. This is one of those questions that, when you look at it, you kind of figure out where you're going. And you go, okay, I need to find the thickness, I need to find the radius, and that's going to kind of take me down a path. And you may not know exactly how to get there, but if you can kind of have this image in your head of the path you're going to have to go down, on the AP exam, you're going to have to make a decision. Is this problem worth the time? I think the problem's worth the time if you really understand fluids, or static fluids. If not, this problem is not going to be worth your time. I'm not going to tell you it's not worth your time in here, but if you're just looking at a straight evaluation of the AP exam, it may not be worth your time to do so. So that's essentially the problem. Hopefully I answered all of that question as thoroughly as I could. Have a good day.